our first PyData Montreal meetup of 2021. So today we have two speakers. So the first presentation will be on scaling machine learning with Python and Dask by James Lam, followed by a 5 to 10 minute Q&A, depending on how many questions we get. After that, Arnab Biswas will present automated feature engineering on large-scale time series data using tsfresh and Dask. So as you all can see, today's meetup is kind of Dask-oriented, if you wish. So let me quickly present our speakers before I hand it over to them. So James Lam is an engineer at Saturn Cloud, where he works on a team building managed Dask and Kubernetes product. He's a maintainer on LightGBM and has many other contributions to other open source data science project, including Perfect. He holds a master's degree in applied economics and data science. Before joining Saturn, he worked as an IoT data scientist at AWS and Uptake. And Arnab Biswas, he is a data scientist working on in Eco Energy and Carrier Global Corporation. So about 15 years back, he started his career as a software engineer. And over the years, he worked at various organizations such as Cisco and Nokia and other companies working kind of telecom and networking domain. His current area of focus is machine learning for predictive maintenance in HVAC industry. He has worked as well as volunteered for different nonprofit organizations in India, helping them address their data science related needs. So before I hand it over to our speakers, so our traditional slide. So here you can see a link that will lead you to a Google form that has only a few questions. Questions are about your interest, as an audience of PyData Montreal meetups, that will help us kind of tune the topics that we cover, the speakers that we invite for future events. So the upside of filling out this survey is that you will get a chance to win one of 2 annual JetBrains licenses for any idea of your choice. So it's really a win-win for everyone here. So that's it for me. And James, the floor is yours.
Okay, great. Thank you so much. Let me just share. Okay. Can you see my slides okay? Are you able to see my slides?
Yes, we can see your slides.
Yes. Okay, great. So thank you so much for that introduction. I'm here today to talk about scaling machine learning with Python and Dask. So let's just get right into that. And as was mentioned previously, I work at a company called Saturn Cloud. So most of what you'll see in this presentation today is working with Dask, only using the open source components of Dask. At Saturn, we have a managed Dask offering, which is basically we run Dask and do some of the hard parts about it for you, and you can just play with it. Okay. First, I'd like to just talk about why Dask. Why would anyone use Dask in their project at all? Let's start with the world of doing data science in Python without Dask. So data scientists, they love Python for exploration and machine learning, and there are all of these amazing libraries that you can use in Python. Scikit-learn, Numpy, Seaborn, Pandas. I'm sure that maybe some of you in the audience have used some or many of these. But the issue is that many of these libraries, they were designed only to work on one machine. And that means that those libraries are limited to the physical resources of that one machine, which might be your laptop. And so that means that if you have a problem that requires a larger data set, those libraries might not be the best choice for you. And when I say larger data set, I don't only mean more rows and more columns. I also might mean a larger problem. Like you're working on a machine learning problem and you want to do many, many, many different combinations of algorithm and hyperparameters and features, or you want to do many training iterations over the same combination of those. And so when you get into those situations where you're working with a larger amount of data, those libraries, though they have really friendly and familiar and comfortable APIs, they might not be the right solution for you. You might need to scale out. To give you one example of this, if you've never read the blog post or seen the famous talk by Wes McKinney, 10 Things I Hate About Pandas, I really, really recommend that you look up that blog post. And in it, he talks about some of the features of Pandas and some of its limitations. And one of the things that he mentions that really stuck with me is this idea that you need to have 5 to 10 times as much RAM as the size of your data set to work with that data in Pandas. This will be the same for other kind of PyData libraries that you use, that they can be possibly very memory hungry, and it's not too hard to find yourself working on a problem where those libraries are not able to handle the size of the problem you really want on your laptop or on the machine that you're working on. And so when you find yourself in this situation, you have a couple of options. The first option is to just convince yourself that you maybe don't need as much data. And there are tons of tools for doing this. There are a bunch of data warehouse tools like Snowflake, like BigQuery. There are SQL over files types of tools like a Drill, Presto, Amazon Athena, things like that. And there are batch scheduling projects. You can use Spark SQL to write SQL over files. There are other projects, Hive, things like this. And in all of these projects, you're basically saying, I'm not going to have all of my data here on my laptop. I'm going to put all my data somewhere else. And then I'm going to use these tools to go basically write queries over it and give me a chunk of that back in my Python session. And maybe downsample things, maybe take averages, do whatever you're going to do. Another option that you have to work with more data is just to get a bigger machine. So you can go to any of the major cloud providers and spin up a VM, run Jupyter notebooks in there, and get like a pretty large machine. But that's going to cost you some money. And as you get into the larger instance sizes, you can start to face problems with availability from those services and with capacity. One other option that you have for working with larger data sets or larger problems is to use more machines. So instead of getting one big box, to kind of bind together maybe many smaller, cheaper things. And there are lots of options for this in the machine learning space. So LightGBM, XGBoost, and TensorFlow have all implemented their own baked-in distributed training libraries, distributed training frameworks that are completely tightly coupled to those projects. And then there are other more general purpose projects like Ray, Dask, Kubeflow, MLlib, which will allow you to look at a lot of different types of problems, work with different types of data, use different sorts of machine learning algorithms over multiple machines. So these are kind of the options you have to work with. Downsample, get a bigger machine, or use more machines. And as I mentioned, some frameworks have implemented their own stuff. So that's like XGBoost, LightGBM, TensorFlow, PyTorch. When you do distributed training in TensorFlow, distributed training in XGBoost, you're using parallelization code that those frameworks wrote. And what that means is that you have to kind of play within the rules of those frameworks. You will often find, though, working on data problems, that those machine learning training libraries they don't offer enough flexibility to do the things that you need. So for example, if you need to write some custom code to pull data from another data source, or to combine your data sets in different ways to do feature engineering, you might not find the support that you need for that in those machine learning libraries, which were really mainly focused on training and evaluating models and not necessarily data munging. And so two very popular tools for doing that sort of more general purpose distributed data processing are Apache Spark and Dask. And Apache Spark and Dask, they both have similar aims. So I could talk for hours about the comparison between these two tools. And I also think there are people who are much better qualified than me to compare them. But I want to just give you a little flavor of what they each do. So first, let's talk about how they're similar, because there are a lot of ways that these two tools are very similar. So both Spark and Dask offer distributed training. So in Spark, you can use Spark ML or MLlib. You can use the MML Spark project from Microsoft. Some specific projects have their own Spark implementations, like the XGBoost for JSpark project from XGBoost. And you can do the same in Dask. Dask has a project called Dask ML for distributed training, and some other things, XGBoost, LightGBM, tsfresh, things like that. They also both have distributed data structures. So when I say distributed, I mean your code is operating on data that is spread over multiple physical machines. And it's controlling processes running on multiple physical machines. And so in Spark, maybe for some of you who've worked with Spark, you've seen these data structures like the data frame, the distributed matrix, the RDD. These things look to your code like they're just a normal kind of data frame or list or something sitting right there in memory on your one machine. But what actually happens is Spark turns commands on those data sets into kind of distributed processes that are over multiple machines. Dask has the exact same thing. There are a few important differences between Dask and Spark, and I want to kind of call those out. So the first one is that Dask is a Python-first project. For those of you who've written Spark or worked in PySpark, I'm sure that you've had that experience of you test some PySpark stuff, you're feeling really good about it, you change one thing, and then your terminal is like spitting fire at you, and that fire is in the form of a 100-line Scala stack trace that you don't understand because you're a Python developer and you write Python. You may have other bad experiences with Dask, but you will never have that experience because Dask is Python all the way down. The next really nice feature of Dask is its API parity with the PyData libraries. So you don't really, when you work with Dask, when you work with Dask DataFrame or Dask ML, you don't have to feel like you're writing Dask code. And so the Dask DataFrame, for example, has an API that is very, very, very similar to Pandas. And its goal is to be, 100% the same. But of course, there's always a couple of, small strange things. But for the most part, Dask DataFrame code looks just like Pandas code. For the most part, Dask array code looks just like Numpy code. Dask ML's grid search CV looks just like scikit-learn's grid search CV. And so what that means is if you've been prototyping things on your laptop or on some other kind of smaller workspace, and you want to use Dask to expand the size and the scope of what you're doing, you shouldn't have to you shouldn't find yourself doing a ton of rewrites and changing a lot of your code. One way that the Dask ecosystem guarantees this is that some of the kind of core contributors in the Dask ecosystem are also contributors and maintainers on those PyData libraries, on Numpy, on Pandas, on scikit-learn. And so I think you'll find that you can switch to Dask without needing to do a lot of extra rewriting of code. The next nice thing that Dask offers is finer grained control over the task graph. So in both Dask and Spark, when you describe an operation such as take this data frame, group by the values in this column, and give me the mean for each group, something like that, both Dask and Spark are going to turn a command like that into an ordered graph of operations. And so by ordered, that means they may first do some work to identify the groups. They may shuffle data around so that data from each of those groups is physically co-located. They might calculate the means, and then there might be a step where they compute those means and bring them all back into your program. The difference between Dask and Spark is that in Dask, you can do very weird, heterogeneous task graphs. So in Spark, everything is built around those functional programming mainstays like map, reduce, group, filter, and others, where it can be a little bit difficult to do highly custom things to say, if this condition is true, go down this weird processing path, but this also interacts with this other thing. Dask allows you that finer grained customization. So any flowchart of a directed acyclic graph that you can imagine drawing on a piece of paper, you can implement in Dask and rely on Dask to parallelize, which is kind of cool. And then finally, Dask Array supports multi-dimensional arrays. So if you're working on problems that require multi-dimensional arrays, you're going to have a better time with Dask Array than you would with the matrix equivalent in Spark. There are also some reasons that you should prefer Spark to Dask. So this is not like a slam dunk, Dask is always better no matter what situation. The first is support for SQL, and this is a huge one. one of the reasons that Spark has been so popular and has ingrained itself in so many organizations is because of Spark SQL. This ability to write SQL over files in a distributed file system, in something like HDFS or something, is extremely, extremely powerful. Because of Dask's flexibility, it's a little bit difficult for the Dask project to have a performance SQL over data frames offering, and so they don't. There are a couple of interesting projects that are in process right now. There's a project called Dask SQL. There's a project called Blazing SQL. There's a project called Fugue, but there isn't really a clear winner between those, I would say, yet. And you'll definitely you won't find anything quite as mature as Spark SQL. So if you're writing a lot of SQL, Spark might be your friend more than Dask would. The next is some high-level optimization. So because Dask is so flexible, it puts a lot less guardrails on the computations that you do. And that lack of guardrails means it's harder for Dask to look ahead at your execution graph and just know what you mean and make changes to optimize, to get rid of unnecessary work, or to reorder things to reduce memory usage. Spark can do a lot more of that stuff because it's better defined. So if you're doing kind of things that really easily fit into the Spark paradigm, like a lot of mapping, reducing, filtering, things like that, you might find that Spark is more performant, possibly. Next, Dask does not have as mature of a distributed graph data structure library as Spark. So in Spark via GraphX, if you're solving graph problems, you might find that there have been more people who came before you and have done that effectively in Spark than you would find in Dask. And then finally, Dask is extremely focused on Python. And so if you're working in Python, that's great. Your Python stuff is going to work with Dask. You're going to be able to accomplish really cool things. But if the majority of your code base is in something else, if it's in one of the JVM languages or it's in R, you're not going to have a good time trying to move that to Dask. You can do things in Dask. There are libraries for calling R and Java and Scala code from Python, but you're going to find that you are outside of the normal Dask experience and kind of on your own with that. So if most of your work that you're doing is in Scala or in R, Dask is probably not the right choice for you. Okay, so I know it's horrible when you go to conferences and people show you benchmarks. So take this for what you will. We've done a little bit of work at Saturn benchmarking the performance of Dask and Spark. And at least for one case where we were looking at using grid search over different hyperparameter values for elastic net regression, we found that Dask really outperformed Spark, even on the exact same hardware from AWS. There are a variety of different reasons for this. The TLDR of this is that we found that because of Dask's flexibility, there were some things where it was able to start on the next piece of work, where Spark had kind of like synchronizations and a little bit of blocking where it was waiting for experiments to be done. But again, I take this benchmark for what you will. Okay. That is all that I want to say about Dask versus Spark. Again, we could go on forever about this, but I'm not really an expert on it, and you don't want to hear more about it anyway. If you want to learn a lot more about this, the Dask developers have written up this comparison to Spark document. You can find it at the link that's shared here, and I'll share the link to these slides at the end of the talk, and you can go there and look for a lot more detail. Okay, so that's why Dask. Let's talk about what Dask actually is. Dask works really easily on one machine, and that's really awesome. You should try it. It's great. But for this talk, I want to focus on using Dask to control multiple machines. So let's get into that. So first, Dask is not one library. Dask is an ecosystem of libraries, and they all have different responsibilities. And so throughout the next couple slides, you're going to see notation like this, where I have a name in purple in these brackets, and that refers to one of these libraries from github.com/Dask, from the Dask organization. Okay, so let's talk about distributed. So the distributed project implements a scheduler for Dask that knows how to take work that you've described and have different worker processes, which may be running on multiple physical machines, do that work. And so what happens is you do some work in Dask, And that, when you describe that work, it creates a graph of tasks to be completed. And then the scheduler takes those tasks and divides up which worker is going to do each of them. It gives those tasks to the workers, and then it asks the workers, hey, did you do it? Hey, did you do it? And it tells your code in a notebook or something like that, hey, the workers did it. That's the basic idea with distributed. And so Dask has this really nice separation between the client object, which is what your code talks to, this scheduler, which knows how to control workers, and these workers, which just know how to take instructions from the scheduler and do stuff. And I'll show you in a second how this separation allows for you to plug in different choices at each of these levels. Before we go farther, though, I want to make a key point. This was something that confused me when I started working with Dask. When we talk about workers in Dask, worker is not a synonym for machine. So a worker is a physical, it's a CLI process. It's a process on your computer. And you can just, if you pip install Dask, you can run a bunch of these Dask worker processes right on your laptop. And so what this tells you is you can have a Dask cluster with 3 workers just sitting on your laptop. It also means if you have 3 physical machines, you can have 6 workers spread across those physical machines. So that's a really important thing to remember, that the Dask scheduler and the Dask worker are processes, and that when I refer to workers, it doesn't necessarily mean individual machines. Okay, so remember I said a minute or two ago that that separation between the client and the scheduler and the workers means that you can plug in different options. Well, one of the places where people have learned to plug in these different options based on their own needs is in the different types of schedulers and workers. So all of these projects exist to run Dask on different types of infrastructure. So for example, if you already have a Spark cluster, or maybe you're running Spark on Amazon EMR or DataProg from GCP or something like that, you can use the project Dask Yarn, and that will use Yarn as a scheduler, to negotiate resources, figure out where the workers are, and you can just run all your Dask code on your Spark cluster. No new infrastructure required. If you have a high-performance computing cluster, maybe you're using some other job queuing system on there like Moab or Slurm, you can plug Dask in there as well with Dask MPI or Dask Job Queue. So again, no need to get new infrastructure, which is cool. If you are comfortable deploying to Kubernetes, whether that is in a cloud provider, whether that's on-prem, whether that's micro K8s or something like that on your laptop, you can use the Dask Helm chart or Dask Kubernetes. And what this will do is it'll create a pod in your Kubernetes cluster, which acts as the scheduler. And then the scheduler will know how to create additional worker pods. And so you can do all the cool Kubernetes-y things like setting up auto-scaling and having Kubernetes taking care of failure recovery and all kinds of cool things. And then finally, if you want to do your work out on Kubernetes on a cloud provider or on other VM management tools on cloud providers or container management tools, you can use the Dask Cloud Provider library. This library is really exciting. I have seen this library grow a lot, even just in the last 4 or 5 months that I've really been paying close attention to it. And now you can use this library to get a Dask cluster running on GCP, on AWS, on Azure, on DigitalOcean. You do not have to use Kubernetes, but you can use Kubernetes. You can use Fargate, Azure ML workspaces. I know I'm just kind of saying a bunch of words, but what I want to convey with this slide is there are many, many, many ways to run a Dask cluster. And many of them overlap with the ways that you're already used to running other distributed applications. Okay, so let's go a little bit deeper into what Dask does and how it works. So all of the work in Dask is arranged in an ordered task graph, kind of like I mentioned above. And setting up that task graph has 5 steps. So the first step is construction. And in construction, you're not actually doing any work yet. You're just kind of setting up the graph. And this is literally just a huge Python, well, possibly huge Python dictionary where the keys are identifiers for the tasks and the values are function calls and their arguments. After the graph has been set up, there's an optimization stage. I mentioned before that Dask doesn't have quite as powerful high-level optimizations as Spark, and that's true, but it doesn't mean that there's no optimization. So Dask has some ways to look at the work that you're doing and to identify either redundant work or work that could reduce the total memory usage or communication overhead, just without changing the functional behavior of the graph, something like that. So once the graph is constructed, Dask will do a little bit of optimization. After that, it's going to do serialization. So all that means is the client, which you can think of as just like a Jupyter notebook on your laptop or something, that client is going to take the graph and send it to the scheduler. And the scheduler will then tell the workers about the graph. It'll tell the workers, hey, here's the stuff that we're going to work on next. Then you get to the scheduling point. In the scheduling point, the scheduler says, all right, I've built the graph. I've optimized it a little bit. All the workers now understand what I'm talking about when I say run task 1, 2, 3, 4, 5. And so I'm ready to start doing the work. And the scheduler will look at the available workers. It will look at what other work they're doing right now, their available CPU and memory. You can get the scheduler to look for specialized resources like specific workers with GPUs. And then the scheduler will say, all right, it's time to start doing the work. So this is where it becomes important that the graph is ordered. Because in this example, the scheduler is going to say, okay, I know we have this task INC. This relies on this output Y, but before we can get Y, we have to run this task add, which relies on this input Z. So I need to tell a worker that has access to Z to run add to produce Y. Then we can run INC, et cetera, right? Once that scheduling is done, then execution starts. Workers get these instructions from the scheduler, like please run task 1, 2, 3 and create result Y or whatever. And the workers just start doing the stuff. They just run your Python code. They output logs. They output some diagnostic information about their memory utilization, their CPU usage, and then the work just proceeds. If those tasks fail, the scheduler has some idea of how to restart those tasks, maybe to move them to other workers. If workers fail, then the scheduler will understand something about which work has not yet been done and ask one of the other workers that's still alive to do it. And this is kind of the magic of how Dask works. Okay, so if you want to create your own Dask graphs, if you don't want to use one of the higher level libraries, you can use a project from within the Dask ecosystem called Delayed. And in Delayed, what you do is you write Python functions, and then you wrap them in this function Delayed, or you can use a decorator. And this basically sets up the graph. So this example is taken directly from the Dask documentation. And I've cut out a couple things to make it look pretty on a slide. But the key point here is that running all these things that are like dash.delayed, 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 this is building up a graph like this. And so what we're saying here is we have this final output. It relies on this function called sum. Before I can run sum, I need these 5 inputs. Well, these 5 inputs come from these 5 function calls. These 5 function calls, each of them needs 2 inputs. And those 2 inputs each come from some other function call. And so in Delayed, you can set up the graph without executing it. And then you can choose to tell Dask, okay, please execute the graph now and give me the result. So you have very, very fine-grained control over parallelization, which is cool. Let's go one level of abstraction up. So let's say that you tell me, James, I really don't want to write my own Dask graphs. It kind of sounds like a lot. I just have some Numpy code or some Pandas code, and I want to run it on a bigger data set. Totally fine. Dask has you covered there too. So Dask has these higher level collections called bag, array, and DataFrame. A bag is similar to what you might see in a Spark RDD. It supports those functional programming operations like map, filter, and reduce. So think of that as just kind of a collection of data that is iterable. The Dask array is a distributed array that has a very similar API to Numpy. And the Dask data frame is a distributed data frame that has an API very similar to Pandas. And when I think about these, I really, really like this figure from James, from one of the Dask developers. I can't technically say this is in the Dask docs. When I took this image, it was from a GitHub issue that's linked in the speaker notes of this slide, but you can basically consider this the Dask docs. And this shows what's kind of happening. So in a Numpy array, forget about Dask for a second. you have an array with 6 numbers in it, right? When you call .sum, they're all right there in memory in one process. You add up the 6 numbers and you get back the sum. Well, in a Dask array, this logical data might be split up into multiple smaller Numpy arrays. So here I have 2 chunks, one with 4 and one with 2 numbers. And so when you call .sum on a Dask array, well, Dask array is going to know that the sum of all of the data is the same as the sum of the sum from each chunk, right? And so what Dask will say is it'll create a little task graph that's like, okay, chunk 1, I need your sum. Chunk 2, I need your sum. And these chunks might be owned by different workers. And then that data is going to be summed and returned back to the process that called sum on Dask array. So just think about it like this. A Dask data frame, it looks and feels like one data frame, but it's actually many little Pandas data frames. A Dask array looks and feels like one Numpy array. It's actually many smaller Numpy arrays. And you can control, when I say many smaller, you can control how many chunks your data gets split into, how they get split, all kinds of cool stuff. Okay, cool. So we've done low-level graph. We've done these data collections. The next level of abstraction up is higher-level workflows like machine learning. And so there are a couple of interesting machine learning extensions that developed in the Dask ecosystem. And that's Dask ML, and then the Dask XGBoost and Dask LightGBM projects. So in Dask ML has an interface similar to scikit-learn. And what you do in Dask and Dask XGBoost and Dask LightGBM kind of adapted that same interface. And if you look at this code, it should look familiar to those of you who've used scikit-learn, right? It just looks like your normal set up a regressor, call fit. But the key takeaway here is that the input data don't have to live on the machine where this notebook is sitting. Those input data can be a Dask data frame or a Dask array. And so what will happen is you just use this code that you're familiar with, and it'll turn into a more complicated Dask graph that Dask will then execute. And you can execute that on any of those Dask integrations that I talked about before. I'll show in a little bit the project that will hopefully soon replace Dask LightGBM. And Dask XGBoost has also been replaced. But I kind of wanted to call these out because these 3 things kind of grew up together and they kind of have similar ambitions. Okay. All right. With that, I'd like to show you a live demo of some of the Dask stuff with LightGBM. Hopefully it works. So let me take a look. Okay, looking great. All right, so if you've ever watched a cooking show, you have probably seen when you're watching the show and people describe, how to make a turkey or how to do whatever, and they say, put the turkey in for 8 hours, and then after the commercial break, the turkey's done, right? I've done a little bit of work ahead of time to get this demo ready. However, this demo is publicly available on my GitHub. You can go to github.com/jameslam/talks, and you can run this yourself. It uses all open source components. It has a permissive license. So I promise you there is no trickery here. This demo will really work for you. Okay. And so first, let's look actually at a local example before we try the AWS one. So what I'm going to do here is I'm going to show you how to use Dask LightGBM on a local cluster. And so a local cluster in Dask, this illustrates the point that I talked about before, where workers don't necessarily have to imply machines. So in this case, I've created a 4-worker cluster, sitting here on my laptop. So if we expand this, you can see that the IP addresses, let me make this a little bigger. You can see the IP addresses here are all just my laptop, right? We're all just hanging out here inside this container on my laptop. And each of the workers, I have 8 total threads available. And each of the workers has been given 2 of them. And you can see they each have like a certain amount of memory that they're allowed to play with. Okay, let's come back. This point right here, this cell where I've run local cluster, this is going to be the only point in the rest of this code where anything needs to know whether this Dask cluster is on my laptop or on AWS or on like a rack of Raspberry Pis in my basement or whatever. right here in the way that I set up the cluster and the client. Every Dask cluster will give you the ability to look at this diagnostic dashboard. So this is not specific to the local case. This is what I want to look at next. Actually, let's go side by side here. Okay, so in the Dask diagnostic dashboard, you're going to see a couple things. You can see a little bit of information about each of the workers, their IP address, the ports that they're communicating on. If we had any tasks running, which we don't right now, you would see them running here. In the System tab, you can see information about the scheduler. Scheduler is not really doing very much right now. Once we start running some tasks, you'll be able to see a graph here of the order of those tasks. And then we can even go all the way down to the individual workers' logs if you want. And you'll be able to see that as well.
James?
Yeah.
Sorry to interrupt. Could you please zoom in a little bit? The text
Sure.
is a bit blurry and it will help. Thanks.
Yes. Of course. Let me go back to... Okay. Is that better?
Yes, thank you.
Okay, sure, no problem. Yeah, interrupt me if anything else is hard to see. Okay, so let's do something. So here I'm going to use a library called Dask Array. I've imported this as DA, and this should look familiar to you. This should look very similar to Numpy code, and I'm just going to create two random arrays. This first one called data is going to have 1,000,000 rows and 100 features. And I'm going to split it into 10 pieces. Remember those chunks that I talked about before. Okay. And notice that that ran immediately, right? That ran extremely quickly. Well, the trick here is that Dask hasn't really done much yet. At this point, we're still in the construction phase of the graph. So if I go look at the worker memory, there's still nothing here. There's like no data here at all, right? 50 megs is nothing at all. And that's because these are lazy. So if I print data right now, it's just going to show me this graph thing, and it's going to be like, okay, I'm ready to do stuff, but nothing has actually happened yet. So to do that, I'm going to run a function called persist. This isn't strictly necessary, but I like to do this so that when you look at the training, machine learning training, you can figure out how long the training took versus just how long the data setup took. So when I run persist, this is going to execute a bunch of tasks to create all of this random data. And it's going to store that in memory on the workers. Then this wait command is saying, don't move on, basically block the execution of this notebook until all of those tasks complete. So let me do that. It's going to be pretty quick. We have a bunch of tasks running here. These are doing random sample things, whatever. And we should see now when we look at our workers that they have a lot more data in memory. Remember, we had about 50 megabytes in memory before, and now we're in the range of 200 to 300. So our data have been set up, and now we're ready to do some stuff. Okay, next I'm going to set up this Dask LightGBM regressor. So I imported this from LightGBM, and I think it's at this point that I should make a very important point. The Dask support in LightGBM is not available in any released version of LightGBM. So we had this pull request in November of last year to take the contents of this project, Dask-LightGBM, and merge it into LightGBM. So right now I've built this image from source of LightGBM. So if you go to LightGBM and you kind of clone down the repo, you'll be able to see this. This will be available from the LightGBM package that you get from pip install LightGBM in the next release of LightGBM, which you should expect in weeks, not months. I'm not exactly sure when. Or you can just follow along, try this out yourself after the talk in the examples at this repository. Okay, so now that you know that I'm not cheating here, let's fit a model and let's go see what happens. All right, now the workers are doing stuff. CPUs are maxed out. Let's look at the tasks that are going here. Let's look at the graph. Okay, so check this out. Here's our graph. Those four tasks at the end were each training task. So what happens is when LightGBM uses distributed training, each worker in the Dask cluster contribute to training based on the chunk of the data that they have. I have written a bunch more about this. I forgot to share this link. I've written a bunch more about this in this tutorial. I'll put this in another for those who want to copy it down and a little bit easier to see. I've written about this in detail in this tutorial, and then you can also find this in the built-in LightGBM documentation. But what's happening here is LightGBM is a tree-based model. It's a boosting algorithm, and so what that means is that each tree has to be completely done training before the next one is trained. And so the work that's being parallelized here is evaluating all of the possible splits and deciding which node will be added to the tree next. And so the way that LightGBM training works is it'll have, in distributed mode, is it'll have these 4 tasks kind of all running at once. But that has already completed, which is cool. And we can see some stuff. We use Dask to fit this model, but the Dask LightGBM regressor and Dask LightGBM classifier, both of these come with a method called toLocal, which will allow you to get back the scikit-learn equivalent. So even though I used Dask for training, I can easily extract out of there the regular kind of single node scikit-learn model. And that's really important because it means that when you deploy this model, you don't need to take on Dask as a runtime dependency. So if you wanted to use Dask to train on a large amount of data, but then your deployment is very lightweight, you don't need to have Dask. You can just get a normal scikit-learn regressor, or if you want to go even lower level, you can get a normal LightGBM booster. And then you can do all of the normal stuff that you're used to doing in LightGBM on this booster object. So once training is done, there's nothing Dasky and special about the model anymore. You can do all of the visualizations and extracting the model and all of that stuff that you want to do. Okay, I think that in the interest of time, I won't go through the AWS example, but if you're curious about going further than kind of working on your laptop, I have this other example notebook that will show you how to create a cluster on AWS Fargate. This example will build a Docker image and push it for you. And I just want to show you that in this code, remember what I said before, that at the point of setting up the client and the scheduler, that is usually the only place where your code needs to change based on how you're running Dask. And that's true in this example too. So I've imported this library called Dask Cloud Provider. Dask Cloud Provider has all those options for running Dask on different cloud services. I'm using a service called AWS Fargate. Think of AWS Fargate as it has similar ambitions and goals to a project like to Kubernetes. But what it does is it runs a bunch of virtual machines, EC2 instances. It runs the Docker daemon on each of them, and then it schedules Dockerized tasks onto those VMs. So this is the only part of the code that really had to change. And otherwise, all the rest of this code for training a LightGBM model looks exactly the same to the on my laptop version that I just showed you. Okay, let's come back. So I want to be sure that I remind everyone again that you can try these demos yourself. And I really encourage you to try these demos yourself. I especially would appreciate if you try the LightGBM demos and find bugs and report them on LightGBM's repo. I would be very, very, very grateful for that. And so you can do this one of two ways. If you want to do this completely on your own infrastructure, on your own laptop, you can clone this repo and run all of these examples yourself. They don't require any proprietary stuff. You don't have to spend any money on AWS to run them. Or you can come try a free trial of Saturn Cloud. We have, if you go to saturncloud.io, you'll see we have a project called Saturn Cloud Community where you can go in and try things out. And we have a LightGBM project that you can work on. It has notebooks similar to the ones I've just shown. You can use Saturn to create a Dask cluster. You don't even really need to think too much about the Dask stuff, and you can just kind of play around with it. So both of those options are available. That is the extent of what I wanted to talk about today. I would be happy to take questions whenever we do Q&A. And after the talk, please feel free to contact me at any of these places. And I'd be happy to answer any questions you have about contributing to open source, contributing to LightGBM, using Dask, or whatever I can answer. Thank you so much for your time and for your attention.
Thank you, James. It was a very interesting talk, and we're happy to have you as a speaker today. There have been a couple of questions in the chat. And I think Alex has a couple of questions too.
Okay.
So the first question from the audience was, how Dask helps in ML machine learning applications, since we're already using GPU for faster training and inferencing?
Okay. So the question was basically, if I care about training speed, why would I use Dask instead of just getting a GPU machine? And the answer is that there are great Dask projects that you can use to use multiple GPUs at the same time. So there is a set of libraries available from NVIDIA called Rapids. You know, I should have known that just Googling that would not be enough. There's a set of libraries you can use from NVIDIA called Rapids. And one of these two of these that use Dask are QML and QDF, which allow you to basically use Dask to create Dask data frames that live in GPU memory and to train models using model estimators that have all of the core algorithm implemented in CUDA kernels to run on the GPU. So using Dask and using GPUs are not mutually exclusive. And actually, if you try out, one of the things that we've worked on a lot at Saturn is making that experience easier. The other thing that I would say is speeding up training is not the only reason to consider using Dask for machine learning. So another reason to considering using Dask is if the amount of data that you're working with is larger than the machine that you can feasibly get. And feasibly get might mean, you know, you're bound to only your laptop. Maybe you're just doing research. You don't have money to spend on the cloud. Or it might mean, you know, even in the cloud, like once you get to a certain size of instance, it can become prohibitively expensive to run those things. So one of the advantages of Dask is that you get some training speed up through parallelization. Another advantage is just that it removes that upper limit on the amount of data that you can work with. I hope that answered the question.
I think it does. So the next question is, for the benchmark of Dask against Spark that you have shown, how many times did you run the pipeline for each configuration presented in the chart? Or is it an average?
That is a great question. The benchmark that I showed, and again, every one of you has a right to be skeptical of benchmarks shown in conference talks. The benchmark that I showed was an average over 10 runs. We have some more details available on the Saturn blog about that benchmark. Take that for what it is. Honestly, I would tell you that speed of execution between Dask and Spark should not be the only reason that you consider using Dask instead of Spark. For me, the reason that I really fell in love with Dask over Spark was because everything is in Python. It was because of the care that's taken to make the APIs look similar to Pandas and Scikit. And it was just because it was a lot more extensible and kind of easier for me to customize than I found Spark to be.
Like you mentioned, there can be reasons to prefer Spark. There can be reasons to prefer Dask. And as usual, it depends.
Of course. I know it's always like a little frustrating to hear speakers say like, well, it depends, but you're totally right. It does. I think there are a couple of rules where you can be pretty sure, like if the only work you're doing is SQL over large data sets, stay in Spark. But there's a pretty large kind of blurry area in the middle.
Yeah. A couple more questions from the chat.
Sure.
For Dask ML, the model can be saved in the same format as scikit-learn. Is that correct? Yes.
So when you use Dask ML, I should be clear. What Dask ML will do is it'll allow you to take scikit-learn models and basically train them in parallel on different parts of the data, and then ensemble together those results. So the Dask ML project, you're not going to find like a Dask ML k-means that's a Dask implementation of k-means or something like that. And so what that means is that what you get back is a scikit-learn model. Or in the case of Grid Search CV, you'll get back a set of, say, like the best parameters that then you can use to train a larger model. In some of the other projects, like in XGBoost's Dask integration, LightGBM's Dask integration, and in QML, you will actually get back a model object that is a kind of Dasky model object that contains inside of it a single node model object like you get from scikit-learn that can be, stored with Pickle or Cloud Pickle or something like that.
There's one more question in the chat, and Alex had a couple of questions. But before I pass it to Alex for the rest of the questions, I have one from me.
Sure.
And the question is whether whether you can deploy a model trained in Dask using Dask again. So, for example, in Spark, you can you can deploy the models again in the distributed manner, and whether you have the similar or the same capability in Dask.
Let me ask a clarifying question. When you say deploy, do you mean something like batch scoring, or do you mean something like an on-demand endpoint?
No, it could be like a part of not an ETL job per se, but of a scheduled batched pipeline.
Yeah. Okay. Perfect. So, taking a model and deploying it in kind of a like a job, basically scheduled otherwise, but a one-shot job over all the data is absolutely a great use case for Dask, and it's something that's supported. So the way that would work is you can create one of these Dask data structures, like a Dask DataFrame or a Dask array from the data that you want to score on. And then you can just let me show you an example of this. And then you can take that model object, whether it be a Dask model object or otherwise, and use it to score on all of that data. You can also, in fact, use Dask to take a model that was not trained with Dask and perform scoring over a large block of data. So let me show you some of the examples that we use in Saturn. I'll just show you one that I think will show this pretty well. Hopefully, the GitHub notebook rendering is always like very hit or miss.
You never know, yeah.
Yeah, okay, not going to work.
It's okay, it's okay, yeah.
Not a problem. Basically, what you can do is let's say that your data that you want to score on is a bunch of Parquet files in S3 or something. Dask DataFrame and Dask Array have methods that are from Parquet, from CSV, that will load up that data on the worker, so you don't have to load it all up on your machine and pass it to them. And then the Dask ML's metrics will allow you to compute metrics in a distributed way on Dask arrays and Dask DataFrame, so you can get your mean squared error, RMSE, whatever you want to do without all the data living in one machine. And Dask ML and the other kind of Dask machine learning extensions will allow you to take in Dask collections and kind of score over all of them without all of that data ever having to live in one place. So it can be really nice for that use case.
That answers my question, and I'll pass it on to Alex.
Sure, thank you.
Thanks, James. So I have two questions, probably more from the point of view of beginners and people who are not familiar with Dask.
Okay.
So the first question will be more like a scenario question. Let's say your colleague sends you maybe a link on S3 bucket where there's a giant CSV file. Will be maybe not giant, but definitely a few order, several times more than what your RAM can fit.
Yeah.
Is Dask the first tool that this person should try? Just download the file locally and then kind of run a Dask cluster?
So to the question of, I just got a CSV that's too big to fit in RAM, is Dask the first thing that I could try? That really depends on the problem that you're solving. If you are just looking to do some simple descriptive statistics, you might have a better experience running Apache Drill locally or Presto or something like that. There are Python and R packages for Drill that will let you basically write SQL against a CSV or against a collection of them or against Parquet files. If that's all you want to do, if that's say a bunch of customer transactions and you just want to extract the 100 customers who visited your site the most, Dask might not be the right tool for that. You might find that it's easier to use something like Drill or Presto. But if you want to create maybe views on top of that data, you want to do other stuff with it, I think that it would be worth the investment to write Dask code to do that, because what that means is when you get to larger data sets, that Dask code will already be there. You could also move that data into a SQLite database or something like that. But I think that Dask will give you the a greater flexibility to write custom code and to not be limited by a query language or by the constraints of a particular query engine. So complicated answer. I would say if you're answering simple questions with SQL, just use drill or copy that CSV into a SQLite database or something like that. If you want to write custom code, Dask is a great tool. I should say too, the first time that I learned Dask and the first way that many people learn Dask does not involve about 50% of everything I just talked about. The stuff that I just talked about where you have like multiple workers and multiple machines and you're doing all this stuff, there's like a large group of Dask users who never need to use that, never think about that, and who still do valuable work with Dask every day. And it's because Dask DataFrame, you can also think of it as just an out-of-memory Pandas DataFrame that you use on your laptop. Just like the big memory and big matrix packages in R, for example. So Dask is definitely a good tool to turn to in the question you're asking. It may not be the only or the best one in that case.
Okay, thanks. That definitely answered my question. And the second question is kind of a two-part question. So how much do Dask, like developers who are using Dask, need to be aware about the way that Dask partitions data across the workers in the cluster? And the second part of this question, so once the data is partitioned, how does Dask handle operations that are not like easily or naturally parallelizable? I know, like computing simple things like mean or quantiles or things like that.
Okay, yeah, great questions. So when you're working with Dask, specifically the Dask collections like Dask Array, the question was, how much you have to think about the partitioning. And the answer is it depends on your problem, but Dask's interface for working with it should be familiar if you've used Pandas, and it should actually not be too different from what you might be used to in Spark. So if you've used Pandas and you've done partitioning in Pandas by setting an index, Dask DataFrame will support the exact same thing. So if you set an index on your Dask DataFrame, so let's say that you set a timestamp index, right? That's a really common case. Dask will create partitions based on time. And so when you ask time-based questions, it will know which partitions need to be involved in answering those questions. And it gives you some top-level public methods for changing the partition, for changing the partitioning, for doing partitioning that isn't based on basically a key in your data that's just like, split my data into 10 chunks based on however it's ordered, things like that. So I would say you can do a lot of valuable work without needing to think about that, which is nice. But if you want to think about that, you can, and the way you do it is very similar to Pandas. To the question about operations that require that don't easily fit into thinking about like reducing by key or something, right? That don't easily fit into that case of do a little bit of work on each partition and then combine all the results. I think that you'll find that some of those types of operations that Pandas supports, like applying a function on a rolling set of the data or something like that, there is some support for in Dask collections. In other cases, you might find yourself needing to write your own or needing to compromise. So I can't tell you that there is like a magical Dask thing that makes the problem of the whole data set doesn't fit in memory on one machine go away, but I think that I have found at least that because Dask is so flexible, it is a little bit easier to write custom stuff to work around, maybe what you see as limitations of the framework than it was to do similar workarounds in Spark. So I know that doesn't totally answer the question, but I think that that's the best that I can say about that.
Just to add a small comment to this, I think that they definitely have it in Spark, but I think they have it in Dask as well. There are algorithms to calculate approximate quantiles, for example, where you can set the error that you can tolerate, and then there's an optimized algorithm that is going to give you an approximation. And then the lower the error that you specify, the longer it will take, because if it's 0, it's the whole thing. but I do think that Dask has that too.
That's cool. I didn't know about that. So that's cool.
All right. Thank you, James. And next up, we'll pass the virtual floor to Arnab, who will be talking about working with large scale time series data with Dask.
Okay. I hope you can hear me clear.
Yep.
Okay. So, hi all, welcome. Thank you for making your time out and listening to this session. I am Arnab Biswas. I am a data scientist at the Eco Energy business of Carrier Global Corporation. Today, I'm going to talk about automated feature engineering for large-scale time series data using two Python libraries, tsfresh and Dask. So let's start with the basics. So in time series data, we capture the value of a variable repeatedly over time, resulting in a series of data points indexed in time order. Now, here we have an example. So here we are capturing 10 time series from 10 sensors over a period of time, and each row is associated with a particular timestamp. Now, the most important property of time series is the value of a variable at any instance of time is dependent on the values from the previous instance. So that gives a natural temporal ordering to time series data. And this is the property based on which the time series data is different from the cross-sectional data. In cross-sectional data, we collect the observations from subjects at one point of time or over a particular interval of time. There is no natural ordering. So, say for example, if I had the ability to collect data about the proficiency of Python or R or any other programming language from all the users who are watching this live stream right now, that would be a cross-sectional data. And as you understand, there is no time aspect to it. Now, the most important property of time series, which is the temporal ordering, that brings the biggest challenge. Traditional machine learning algorithms, they are not designed keeping time series in mind. So if I feed a series of numbers representing a time series to a machine learning algorithm, the probabilities are very less that the machine learning algorithm will be able to decode the information hidden in the temporal ordering. Then there are other challenges like non-stationary nature. So often what happens, the pattern or the nature of the time series changes over time. Time series data may get noisy. In an industrial environment, we generally use sensors to capture the time series data, and if the sensor gets faulty, it will start introducing noise. Or what may happen is, if the sensor is capturing the time series data at a very high frequency, then it will capture a lot of redundant information and the signal to noise ratio will come down. Then often what happens is, for a time series task, for example, a forecasting or a classification task, we may have or we will have not one time series, but multiple time series. They may have different sampling frequency. One may be sampled at every 15 minutes, another may be sampled at every, say, 1 hour, and so on. The time series, the different time series may have different different length, like the duration during which they are being captured, that may be different. And finally, time series data comes from different domains. So right now, time series is everywhere. It's in the healthcare industry, it's in the financial industry, it's in the engineering industry, it's everywhere. The nature of the data changes from one domain to another domain, from one use case to another use case. Now, one of the ways to handle these challenges is to use feature engineering. Okay, in feature engineering, what we do is we try to capture the most important characteristics of the data in few metrics. For example, here I have a time series data which has 60,001 observations, and I can start representing that time series data by few metrics like, say, median, mean, maximum, minimum, etc. So that way, what I'm doing is I am taking the time series data, compressing it into a shorter representation. And this is necessary. This is necessary for the machine learning algorithms because, as we discussed, machine learning algorithms may not be able to decode the information hidden in these series of numbers, but it may be able to understand the few matrices which these features are capturing. Now the question is, what features should I use, or which are the features should I try for my task? Generally, what happens is we start with very standard generic features like statistical functions representing data summaries, and then we slowly move into domain-specific features. As we know, domain-specific features are the most important ones. Again, within the same domain, for different use cases, again, one feature would be relevant, another feature will not be relevant. So as a data scientist, it's our responsibility to generate as many features as possible, and then using some kind of cross-validation mechanism, select the features which are most relevant to my task. And this is where exactly tsfresh, libraries like tsfresh, that helps us. tsfresh is an open source Python library. Given with a time series, it automatically generates 750 plus features. And the nature or the type of the features vary widely. There are features which captures descriptive statistical things. And then there are features which comes from the science background, like digital signal processing related features. And of course, there are features which captures the historical nature of the time series. tsfresh also provides feature selection. So given with the time series, I have 750 features. Now, tsfresh provides me a mechanism, hypothesis test based feature selection mechanism, using which I can find out the most relevant features for my task, for my particular target. tsfresh supports parallelization and large data as well, which we are going to talk. Okay, but we are not going to talk about feature selection today. We are going to mostly focus about the automated feature generation. Next, let's take a look of the code. Let's pick up some data and generate the features. Okay, so all my code and this slide is available at GitHub under Arnab Biswas 1, feature engineering with tsfresh and Dask. Okay, so here, I work in the predictive maintenance domain, and where we deal with a lot of time series data, but unfortunately, I can't use those data set. I can't use those data set here. So what I'm going to do here is I'm going to use the data from a Kaggle competition called INGV volcanic eruption prediction. And these data actually contains a lot of CSV files. So in fact, the trained data itself has around 4,000 CSV files. Now each CSV file contains 10 minutes of logs from 10 different sensors placed around a volcano. So this is called a segment. So whenever I use the term segment, I want to mean 10 minutes of time series data captured from 10 sensors. Let's load, let's load one of those segment files and see how the data looks like. Okay. So here we have already seen this data. This data is being captured from 10 sensors. So we have 10 time series captured over a period of time, and we have 60,001 sample for each time series. Here the data looks like this. Next, what I'm planning to do is I'm going to load a bunch of CSV files and or segment files, and then use tsfresh to generate features. Okay. Now, for the sake of simplicity, and also considering that we have limited amount of time for this presentation, I'm going to load just a few files, not the 4,000 ones. Here, what I'm trying to do is, I'm iterating through all the segment files, loading them into Pandas data frame. That means loading them into memory, and then adding them to a bigger Pandas data frame here, appending. So at the end of the process, I'll have basically a data frame having 31,000 rows. So what I've done actually here, again, for the sake of simplicity, I have picked up just the data from two sensors, two time series, and for each time series, I have picked up first 1,000 observations. So here in this data, I have time series from 31 segments. For each segments, I have 1,000 observations. And this is how the data looks like. So here I have two time series, and then there are additional columns like segment ID and time. So segment ID says that this particular observation is part of this particular segment. And the value here under the time column indicates that within this segment, this observation has a time index of 1. So next, what I'm planning to do is I'm planning to extract a bunch of features, okay, using tsfresh. So here what I'm asking tsfresh that, okay, this is the data frame, pandas data frame containing all the time series, and it has multiple segment ID, and within each segment ID there could be multiple time series which you need to figure out, like which tsfresh has to figure out, and then within each time series all the observations are ordered by time. And what tsfresh does is tsfresh generates the features. So here are the bunch of features which tsfresh has generated. If we notice, all these rows are basically indexed by the segment ID. So what tsfresh has basically done is tsfresh has taken all the time series data, which is part of one segment, generated the corresponding features, and placed them in one row. So here in one row, we have all the features related to both the sensors 1 and 4 for a particular segment ID. As a result, when I started with a data frame of size 31,000, having 31 segments data, and my extracted features now have 31 rows. And then we have 1558 columns. That means 1,558 features generated for two time series, sensor 1 and sensor 4. So for each time series, tsfresh has generally 779 features, which is really huge. So now, let's take a look of the features which tsfresh has generated. Okay, so these are the features. There are simple features like median, mean, length, and then there are complex features like C3, etc. To be very honest, I don't understand all the features, and probably that brings a point, right? As a data scientist, maybe there are features which are relevant to my problem or my task, but maybe I have not been able to find out those features during my research work or during my interaction with the domain expert. But those feature works, and hence I should use those. And that's where libraries like tsfresh brings value. So next, what we are going to do is we are going to see how we can control the number of features to be generated by tsfresh. Okay, there is always a possibility that once the feature selection is done, I know exactly these are the features which I need to generate, or I may know well in advance that these are the features which I should not be using. So the list of features to be computed is controlled by a dictionary containing the name of the feature calculator or the feature type and their parameters. Minimal FC parameter is such a dictionary, and it has just eight features. Okay. As we understand, these are very basic statistical functions, and none of them accepts any parameter. So next we'll see another dictionary called comprehensive FC parameter. So this generates around 71 types of features or 71 feature calculators. Now for few features, there is no parameter, and then there are features like this where there are a bunch of parameters. So 71 types of features or 71 feature calculators together with all these parameters are generating 779 features given a time series. So when I extracted the feature here, So what tsfresh did is, out of the box, by default, it uses that comprehensive feature parameter dictionary and generated all the features. Then there is another dictionary. Okay, there is another dictionary which is called efficient FC parameter. And this just drops this doesn't generate the features which are costly. Okay, now I can start with a dictionary out of the box dictionary, and then I can drop the features which I don't want. Or what I can do is I can probably pick up um, the dictionary provided by comprehensive or efficient, and then manually edit it as I'm doing it here. Here, this is nothing but a vanilla Python dictionary, and I can pass that dictionary to using this argument, and tsfresh generates features for me. So I have just few features which I wanted. Next, we'll quickly take a look about the rolling feature. So far, what we have seen that tsfresh has taken a long time series and generated all the features and placed them in one row. But there may be use cases where we need features to be generated on rolling data. To explain the concept, for example, if this is the raw data and then this is the features which are there inside this blue box are generated using the observation which are there inside this blue window. Similarly, the features which are there inside this green box are generated using the observations which are there inside this green window. The window size remain fixed, and as you understand, the window slides for row by row, and for each window we have a corresponding uh, row of feature. So if I have a time series with 1000 rows, the corresponding feature data set will also have 1000 rows. So let's keep this in mind that, well, if I need rolling features, tsfresh has the ability to generate that. Okay, with that, we are kind of done with the basic tsfresh introduction. Let's go back and then let's see. Okay. So now what happens if I have large time series data? I have, say, thousands of time series with millions of observations. In that case, we start hitting two problems. One is large execution time, which is a compound bound problem. And then we start filling the need of larger memory or RAM, which is a memory bound problem. This is specifically to avoid out of memory errors. Now, at this point of time, I want to take a pause, take a step back, and considering all of us are not probably from computer science background, I want to revisit the fundamentals. So we can think a computer as a system made of various components, and one of the component, the computing unit, we can think the computing unit as connected with various memory units like RAM, hard drive, CPU cache using some connectors called bus. And then there is a fourth component called the network connection, which is very slow in nature, but through network connections, a computer connects with the external computing or memory units. Here I have not, I'm not going to talk about GPU, and hence I have not used that. Today we are going to focus only on the CPU. Now, what is happening over years is the clock which resides inside a CPU, the speed of the clock has plateaued. To address that problem, what the chip makers are doing, they have started putting multiple cores on multiple processors within a single physical unit. So now to use this single physical unit or this CPU effectively, what I need to make sure that I utilize all these cores or all these processors in parallel efficiently. That brings us to the concept of parallelism. So in parallelism, we take a problem, break the problem into a lot of small independent problems, distribute them across multiple cores, let the cores compute the partial results, and then combine the results back. Now, parallelism is hard, okay? Because there is an overhead associated with it. Computer takes time to break the problem into pieces, distribute them across cores, recombine them to get the final result. And even harder is developing the parallel code, the code which works in parallel. The good news is most of the data science code which we write using Pandas or Numpy, they can be parallelized better. So far we spoke about computing unit. Now let's talk about memory units. So we have multiple types of memory units inside a computer characterized by read-write speed and then capacity. To start with, we have spinning hard drive. Spinning hard drive has a very large capacity. It's in multi terabytes in general, but it has an extremely slow read-write speed. Next comes solid state hard drive, which has a comparatively smaller capacity but faster read-write speed. Next comes RAM, random access memory, which is even faster, especially when it comes to random data, random access. But its capacity is even limited. It's in the GB range. Finally, comes CPU cache, which is extremely fast, but it has a very small capacity. So CPU cache is important because any data which goes to the CPU for computation needs to go through the CPU cache. So in a computer, we utilize all these different kinds of memory units in an approach using an approach called tiered approach. So there, the data rests in the hard drive. Then we load the data which is just needed for computation to the random access memory. A smaller subset moves to the CPU cache, and even a smaller subset finally moves to the processor. We should note that moving around the data is the most expensive thing, okay? Not compared to the actual computation. The problem becomes serious when we have large data, and the problem becomes acute if we have data that doesn't fit into the RAM. So the question is, if my data doesn't fit into the RAM, is it possible that I remove RAM from the picture and I let processor directly talk to the hard disk? Okay, it looks like that's not an option. That process is going to be unimaginably slow. Something which takes minutes will start taking days. And that's why we have to think about large data strategies. Let's start with the definition of large data. How I define large data is the data that doesn't fit into the RAM. So what would be the strategy? Number one, if possible, just load the relevant portion of the data. That means slim and trim the data so that it fits into the memory. If that doesn't work out, use more RAM. So rent out a VM which has a bigger RAM. If that doesn't work out, then we use something called out-of-core computing. So out-of-core computing is a concept which is being utilized in frameworks like Dask. So let's try to understand it. In out-of-core computing, the data again rests in the hard disk. And what we do is we pick up only one portion of the data or few partitions or few chunks of the data, load it into the main memory or RAM, then do the computation, compute the partial results, and then garbage collect the chunks. Then again, pick up next few chunks or next few partition, load it in the main memory, compute the partial results. And the process goes on like this. At no point of time, we load all the data which is relevant for this problem to the main memory. And that's how we handle larger than RAM data. And finally, we have distributed computing. The idea is simple, that if the resource available in one computer is not sufficient, then use multiple computers. Just connect them. So in distributed computing, what we do is we pick up the data and then break the data into small pieces, send those to different computers, and execute those on different computers. Let the computers come up with the partial result, then one of the computers pick up all the partial results, calculate the final results, and give it back. Now, if I am doing data science with large data, what should be my approach? So if I have a single computer, use parallelization, use multiple cores, make sure that I'm utilizing all the cores available. I should always try to fit the data into RAM. If that works out, well and good. If it doesn't work out, probably use out-of-core computing. And if single computer is not working out, then use distributed computing. Now, the thing is, distributed computing is hard. There may be it's hard to debug, and there may be failures, or it's a little hard. Okay, so if possible, the suggestion would be use a single computer and avoid distributed computing. Now, possibilities are all of us are if all of us are using a VM, we are probably renting out VMs from different cloud providers. This is from Azure, and Azure says that they have um, one VM with 120 cores and 480 gigabytes of RAM. In my opinion, this itself is equivalent to probably one cluster of 30 computers or 40 computers. So now, of course, it costs money, but if possible, then it would be better to use one single instance of computer instead of a cluster of computers. Now, again, let's talk about the challenges when we are doing data science with large data. The popular data science libraries like Numpy and Pandas, they are not designed to scale beyond a single core or processor. So when I'm doing some computation using Pandas, even if my computer has multiple cores or multiple processors, Pandas will not utilize it. They are not designed to scale beyond a single machine. Of course, if they can't handle one core, then probably they are not designed to scale beyond scale for a distributed environment. If I have larger than the RAM data, then I can't use it, because Pandas and NumPy, they expect the data to be loaded into the RAM for any kind of computation. And this is exactly where Dask comes into picture. So I know few portion of the Dask related stuff that may overlap with James' thing, but it would be very minimal. And again, for the sake of completeness of this session, probably let's go through it. Now, what Dask does is Dask parallelizes the Python ecosystem. Okay, so please note this term Python ecosystem. So literally, Dask can be utilized to parallelize any Python library. Using Dask, I can utilize multiple cores. Those cores can be available in one computer, or those cores can be available in a distributed environment across multiple clusters. Dask handles large data using out-of-core computing. That means if the data is larger than RAM data, it loads data from the hard drive as and when needed. Dask scales up on a cluster and it scales down on a laptop. So Dask works on a cluster. Now, if I am not already familiar with Dask, the possibilities are that I'll go back and do the work, write my first set of code on a laptop. And once that code is ready, probably I want to move it to a distributed environment. Using Dask, we can do it without changing much code or without learning a new framework. So let me try to summarize. We are kind of end of this particular section. So if I have large time series data, what I should do? Number one, I should of course make sure that I'm utilizing parallelization. And I should have some approach to handle larger than memory data. Now the good news is tsfresh has get us covered for both the cases. If the data fits into the memory, say for example, if my raw data or my extracted features, they fit into a Pandas data frame, then in case of a single machine, by default, tsfresh utilizes multiple cores. So when I extracted the features here, okay, when I extracted the features here, actually I passed some value for this argument called in_jobs, using which I told tsfresh to utilize this many cores on this machine. Okay. Now, if single machine is not sufficient, tsfresh can distribute the load across a clustered environment. In fact, one of the implementation here is based on Dask. And again, if the data is larger than memory, in that case, tsfresh utilizes Dask and pyspark. Now, this notebook of mine It talks about all these approaches, how tsfresh solves these, addresses these problems. Okay, if you are interested, you can probably go through this particular notebook, or even better, there is a two-part, two-series blog post called tsfresh on large data samples by the author of tsfresh library, Niels Brown, which is even better, right? Which you should go through. In fact, I have picked up all the code from these two blogs and created this particular notebook. However, I'm not going to go through this notebook. What I'm planning to do is I'm planning to discuss how I am using best of both the worlds. Okay, I use tsfresh to extract features, and I use Dask to parallelize the feature extraction process of tsfresh, and also to handle larger than memory dataset. So as we'll see that uh, I have a certain benefit. The features which I'm going to generate for a particular segment or a particular CSV file is going to be completely independent of the features which I am going to generate for another segment or CSV files. We'll talk about it more uh, next. So before we jump into that, again, I want to spend a little bit of time on Dask. So here is how the Dask architecture looks like. James talked about it. The the interface using which an user can interact with a client is interact with a Dask cluster is called a client. The client is where I'm writing the code. For example, the Jupyter notebook is a client. Now this client is connected with a Dask cluster, and the cluster consists of one scheduler and multiple workers. The scheduler actually doesn't execute any job. When it gets a bunch of tasks, what the scheduler does is the scheduler passes those tasks to the workers. Workers execute the tasks, compute the partial result, then one of the workers pick up the partial result, compute the final result, and send it back to the scheduler. Now the scheduler and the worker, they may be located in the same machine, they may be located in different machines. When they are located, when the client, scheduler, and all the workers, they are located in one machine, we call it as a local cluster. And that's what exactly I'm going to do here. I'm going to create a local cluster. Okay. So here, what I'm doing is I'm creating a local cluster with 8 workers. My scheduler runs on 8786, and then I create a Dask client and connects the client to the cluster. Next, whatever computation I do using Dask, those computation will be executed using this local cluster. Okay, so what I'm trying to do here now is I'm going to show the Dask data frame inside the Jupyter notebook. This is the Jupyter Lab extension for Dask data frame. Okay, so next what I tell to Dask is to read few of the CSV files which match this particular regular expression, and Dask does it quite fast. It took around 109 milliseconds. So what has actually happened is Dask has not actually read any data from those CSV files, or it has not yet loaded any data into the main memory. Dask has created a plan to do that. We call that plan as a task graph. Okay, so as a part of this process, Dask has returned us something called Dask data frame. Let's take a look of the Dask data frame. So it looks quite similar to Pandas data frame. It shows the columns, it shows the data types of the columns, and then finally it tells that there are 4 partitions and there are 4 tasks. To understand the concept of partition, let's try to understand how a Dask data frame is constructed. So a Dask data frame is nothing but a wrapper on multiple Pandas data frame. Okay, here the brown box, or sorry, the gray box is a Dask data frame, whereas the black boxes are Pandas data frame. Each black box is associated with one CSV file or with one segment, and we call that as one partition. Since we have 4 CSV files or 4 segments, we have 4 partitions. Okay, so in our case, these partitions are created based on one CSV file. That means the partitions are independent. That means the computation which we do with the data in one partition is independent of the computation which we are doing in the other partition. That's one of the advantage of this use case. Now, just a gentle reminder that so far we have not, Dask has not actually created any Pandas data frame, or it has not loaded any data. So this is regarding our workflow. Now, if I visualize this data frame which Dask has just returned, it gives me an idea what Dask is planning to do. What Dask is planning to do is Dask is allowing one of the workers to pick up one of the CSV file, read the data, and load the content into a Pandas data frame. And this is going to happen for all the 4 CSV files in parallel, done by multiple workers. Next, what we try to do is we try to find out the maximum value of sensor 1 across all these 4 segments or 4 CSV files. When I do this, I get back a Dask data structure. Let's try to visualize it. Okay, so this is how the task graph looks like. Okay, this is how the task graph looks like. Here, one of the workers will pick up one of the CSV file, read the data, load it into Pandas data frame, and then on that Pandas data frame, it's going to invoke this particular function to calculate the maximum value of series 1 within that Pandas data frame or within that CSV file. So that would be considered as a partial result, and here is a partial result. Now this process happens across multiple CSV files by multiple workers in parallel. So at this stage, we'll have the partial results available. So these partial results are the maximum value of series 1 in the individual CSV file. Then one of the workers will pick up all those and then compute the maximum value of all across all the segments and return it back. So as we understand, so at up to this point of time, Dask has just created this task graph, and Dask has not done any computation. Now, the moment I invoke this method called compute, Dask does the computation, gives me back the result, and here is the data structure, or here is the type of the data. This is Numpy float. So two things. One, probably for a moment you saw something here. So when you see something in the dashboard, you should understand Dask is actually doing the computation. Otherwise, Dask is probably building a task graph. Let me try to summarize whatever we have seen so far. So when I'm doing some kind of operation using Dask, if Dask returns me back a Dask data structure, I have to understand that Dask has not done any computation. It has just created a task graph. It has created a plan to execute some operation. Then the moment I do compute, Dask does the actual computation, it executes the task graph and gives me back the result in the form of a non-Dask data structure, which could be a Pandas or which could be a Numpy thing. Now this Pandas and Numpy thing that gets loaded to the main memory. So what we need to be careful that the value which gets returned through this compute, it should fit the main memory or it should fit the RAM. If the result of a compute is larger than RAM, we will hit out of memory. Okay, so this is something which we need to be careful. So next we'll see how can we parallelize a custom Python function using Dask. Here, this is a Python function, and what I do is I invoke this Python function on this Dask data frame consisting of multiple Pandas data frame and parallelize it using a Dask API called map partition. Okay, this is something called embarrassingly parallel process, because here again, here again, uh, the assumption is that the computation which we are doing on one pandas data frame is independent from the other pandas data frame, or the computation which we are doing with the data related to one CSV file is independent of the data related to other CSV files. So what Dask is planning to do here, one of the worker will read the CSV file, load the data into a pandas data frame, and then on that pandas data frame, it will invoke this custom Python function. And at the end of the process, we'll have the result, which is relevant for this particular CSV file. And this happens in parallel. This happens for all the CSV files in parallel by multiple workers. This is exactly what I'm planning to do with the extract feature functions for tsfresh. Okay. So I'm going to take, I will allow one of the worker to pick one of the segment files, then get the pandas data frame, load it into main memory, and execute features on the content of that pandas data frame. So at the end of the process here, I'll have the features for that particular segment. Again, this happens for all the segments in parallel by multiple workers. So at the end of the process, I'll have all the features generated for all the segments. Um, mm, yeah, generated for all the segments. Okay. So which brings us to the actual section. So what generally happens is in a real production like environment, the data would be continuously streaming into um, from the sensors into a data lake-like environment. And then there would be Airflow or any other job orchestration engine which will pick up the data, the raw data, at regular intervals, extract the features, and write back the features to the data lake or to feature store. We'll try to simulate something like this here. We have our data in the hard drive. We'll generate the features and write the uh, features again to the hard drive. So here, what I'm doing is I'm going to use Dask to read the data, the raw data, the CSV files. Then I'm going to use tsfresh's extract feature functions to generate the features. I'm going to parallelize the process of feature generation using map partitions API of Dask. And finally, the extracted features would be written back to the hard drive. So since I'm going to use Dask data frame, Dask will utilize out-of-core computing. And what Dask is going to do is it will allow one worker to pick one segment file, generate the corresponding features, and then write back to the hard disk the generated features. And then the worker will pick up another segment file. And this happens in parallel. At no point of time, one worker is loading all the raw data, or even at one point of time, we are not loading all the extracted features into the main memory, because even the extracted features, the volume of the extracted features may be very large, considering we could have large data, and that may result into a out of memory error. Okay, so here I'm reading the data using a Dask data frame. And here the regular expression is like this: once the matching, starting all the files starting with 1. And as you can see here, we are considering around 2306 partitions. Each partition is related to one segment. Okay, and then we see there are a lot of tasks. Actually, I am doing other stuff also. Here we have the custom Python function, which is nothing but a wrapper on tsfresh's extract feature. One thing to be noted here I have set n_jobs is equal to 0. By that way, I am shutting down tsfresh's out of the box or by default parallelization capability, and I am allowing Dask to take it over. Next here, what I'm doing is I'm passing the custom feature extract feature function to this Dask data frame. This Dask data frame consists of thousands of pandas data frame, and then we are parallelizing it using map partition. And again, I am just generating two features for the sake of simplicity. Okay. So still at this point of time, we have the Dask data structure. That means Dask has not actually done any computation yet. Next, I invoke the function called toParkWait. The moment I do that, Dask actually starts executing the task graph. Okay, and then I partition the data based on the segment ID. By that way, what I am telling Dask to do is, once you generate the features, uh, save the data segment by segment. Okay, for each segment, we should have the generated features separately. Okay, so here, what we can see here is each rectangle or each rectangular line or train that represents one worker. It shows the tasks which are being executed by the worker one after another. And here it shows the tasks. Those are executed here in the task stream. And then finally, let's look at the workers. Okay. So here we have 8 workers. And for each 8 workers, there is some CPU usage, but the memory usage is low. Each worker has around 3 GB of memory limit. Out of that, it's using only 13%. This is because each worker is picking up one segment file at any point of time, loading it into Pandas data frame, extracting the features, writing back the features again to the hard disk. At no point of time, one worker is picking up all the segment files, and that's how we are doing out of core computing. Okay, so if we go back here, we'll see basically that these are the features which have got generated. And if we probably pick up one of those, okay, if we pick up one of those here, we'll see the content, we'll see the features. Okay, so here I'm again using just a Pandas data frame, Pandas, to read the content of one features generated for one segment, and it has, as expected, just 4 features, 2 for sensor 1 and 2 for sensor 2. I can also read all the segment files together, as I was doing for all the CSVs using Dask. In that case, again, Dask will give me a Dask data frame. And next, what I can do is I can use this Dask data frame probably for a training task or for a data validation task or something like that. Again, from Dask data frame also, if I want to do specific computes, I can load the data. In that case, it would be a Pandas data frame. This gets loaded into the memory and I can use it. Okay. So finally, just to repeat, here in this approach, we are using something called embarrassingly parallel mechanism. The features generated for one segment or one partition of Dask data is independent of the another partition, and that's where we can parallelize it much better. So instead of 8 cores, I could have used 64, and things might have been super fast. So with that, I come to an end of the Dask session. Here, okay, again, the code and the slides are available here in my repository. These are few references. We have references for tsfresh. We have references for Dask. And I would like to mention about these 2 particular references. One is High Performance Python book, 2nd edition book, and the Duke University's Practical Data Science course. Using these 2 references, I have generated the material for the fundamental section. I highly recommend them. So with that, I am open for questions.
Okay, thanks, Arnab. So we don't have questions from the audience, but I do have a couple of questions on my side. So first question is, how does tsfresh handle streaming time series data?
I am not very sure about that. I have not seen any API where they are handling the time series data, but I can check and let you know.
Okay. And the second question is, what are other alternatives or similar libraries that are out there that have similar functionality? Because I know for general purpose feature engineering, there's, for example, feature tools library that
Right,
also
right.
is able to do some feature engineering on time series data.
Correct. I think there is another library. I have seen few others. For example, even the tsfresh documentation itself talks about cesium and then fats, and of course the feature
Okay, feature
tools.
tools, yeah.
Yeah. So what I generally, what probably could be a good way is, since we can parallelize the workflow, we can actually pick up multiple tools. We can write our custom function, and inside that custom function, we can invoke the feature generation mechanism for, say, tsfresh, feature generation mechanism for cesium and other libraries, and probably put my own features as well, right? There could be very custom features which are uh, maybe proprietary, and then use it all together.
Okay, and I guess on that note, so tsfresh is used solely for kind of feature extraction and feature engineering, but can it, for example, do anomaly detection in time series, or is it something that you use kind of downstream from tsfresh, like some
Yes,
other
yes.
library?
Right. So what I understand, the goal of tsfresh is to do feature engineering, automatic feature generation. They have a feature selection mechanism as well. But when it comes to when it comes to doing any kind of training or any kind of other stuff, tsfresh is not the library. And in
Okay.
fact, here they have mentioned that tsfresh is not also for streaming data. So that probably
Oh,
answers your
okay.
first.
Gotcha. Gotcha. All right. Yeah, that's all on my side. So, James, I don't know if you have any questions. Maria cannot join because she has some internet issues.
Mhm.
I just have one question, and I apologize if you talked about this and I missed it. Does any of what you did in tsfresh, does it assume that the time series data are evenly spaced in time?
I don't think so. So here what I have done is I have created a 1 minute, one column called time, using which I indicated the time order. But actually, that's not necessary. Even if I don't create this column called time, I'll show you the data which I created. Yeah. If I don't even create this column, what tsfresh will start assuming is all these observations, they are in time sequence, and tsfresh doesn't need a explicit time index like pandas date time or something like that. Okay, there are features which tsfresh generates internally that needs that timestamp, and in that, if I don't have the timestamp, those features doesn't get generated. But in general, tsfresh doesn't need that. Again, tsfresh, it's not that they have written all the custom algorithms. Finally, they are also dependent on, say, the scipy ecosystem to generate the features.
I see. If I could ask that another way.
Yeah.
So in this case, you have like a column 0, 1, 2, 3, 4. And you're saying if you didn't have that, then row 1 would be assumed to be before row 2 in time, et cetera, et cetera. I guess my question is, if I wanted to do like a 5-minute maximum or something, where
Mhm.
because for various reasons, I can't necessarily guarantee that the same number of rows are always going to represent 5 minutes.
Yeah,
Have
that's
you found
actually,
that tsfresh works okay in those cases?
yes, I think so, because that was the actual point, that we could have multiple time series of multiple sampling frequency. And when we are generating the features, we are extracting the features, we try to overcome that challenge.
I see. Okay, cool. Thank you.
Okay. Thanks to both James and Arnab. I think that's it for today. One thing that I want to remind everyone who's still watching, that you can visit a link to our raffle and fill out the survey. to have a chance to win one of 2 JetBrains licenses. And Maria just posted the link into the chat. So again, thanks to our speakers and everyone who joined us today. Bye.
Thank you.
Bye. Thanks for hosting. Bye, Maria.
Thank you. Bye.